Okay, let's unpack this. What if I told you that maybe in the near future, the speed of your electronics, cameras, even quantum tech, what if all that could be controlled not by electricity, but by light? And at speeds we can, well, barely imagine. We're doing a deep dive today into something really groundbreaking. It's about ultra-fast light control for nanoelectronics.
Yeah, and this isn't just, some sci-fi concept. This is solid research. It's based on a peer-reviewed study. It just published actually June 5th, 2025 in Nature Communications.
Right. So our mission today really is to understand how physicists are actually doing this. Why is it such a massive step up in terms of speed? And, what could it mean down the line for the tech you'll actually be using every day?
Okay, so let's get into the core of it, the breakthrough. Researchers, they're from Bielefeld University and also the Leibniz Institute for Solid State and Materials Research Dresden, IFW Dresden for short. They've come up with this new technique. They're essentially using these incredibly short pulses of light, and they use them to manipulate semiconductors that are, get this, atomically thin.
Atomically thin. Okay, that sounds crucial, doesn't it? Because materials at that scale, they just behave differently, right? Light can interact directly with their electronic properties in ways that, well, bulk materials just can't manage. And the idea is to make optoelectronic components controlled by light operating at these crazy high speeds. That feels like a really fundamental shift from how things work now.
It absolutely is. And how they're doing it is fascinating. The team designed these incredibly precise nanoscale antennas. Now, these aren't your roof antennas, obviously. They're tiny structures built to take terahertz light, that's the frequency sort of between infrared and microwaves, and basically transform it into really powerful vertical electric fields.
Vertical electric fields. Okay, hang on. So light comes in, hits these tiny antennas, and boom, you've got these strong electric fields appearing right inside the material, like a semiconductor. How does that work exactly?
Yeah.
Generating these fields. And what do?
Think of the antennas as like optical funnels.
Yeah.
They concentrate the light energy to create these super intense electric fields within the material itself. And they're applying this to those ultra-thin materials we mentioned specifically, molybdenum disulfide, MoS₂. The field strength they're getting is just staggering, several megavolts per centimeter, which, just for context, is an electric field strong enough it could actually rip apart atomic bonds in lots of materials. And this is all generated purely by light.
Wow. Okay, so tiny antennas, powerful fields, all triggered by light. But why is that such a huge leap compared to, what we do now with normal electronics? What's the bottleneck with the old way?
Well, the traditional way, electronic gating, where you apply an external voltage to kind of push electrons around and switch a transistor on or off, that's fundamentally limited. It's limited by how fast those electrons can physically move. It's almost like a traffic jam, There's a speed limit on pushing that current. What Dr. Dmitry Turkinovich, who led the project at Bielefeld University, points out is their way uses the terahertz light itself to generate that control signal directly inside the semiconductor. No external wires needed for the switching itself, in a sense.
Right. That does sound like a powerful shift. But maybe for listeners used to standard electronics, what does it really mean for light to become the gate signal right inside the material? Is there any kind of parallel we can draw, or is this just completely new territory?
In terms of the speed and how direct it is, it's largely new territory. It really is a fresh paradigm. It opens the door to ultra-fast optoelectronic tech that, well, just wasn't feasible before. And the speed, it's genuinely unprecedented for this kind of control. They showed they could control the material's electronic structure in real time on timescales shorter than a picosecond.
Less than a picosecond. Can you just remind us how fast that actually is? Give us a sense of scale here. How revolutionary is that compared to, say, my computer chip?
Okay, a picosecond, that's 1/trillionth of a second. 1 followed by 12 zeros. Your typical modern processor, it operates in nanoseconds. That's billions of a second. So this is thousands of times faster. A nanosecond is 1,000 picoseconds. This research demonstrates control at speeds, thousands of times faster than current electronic switching. And they could selectively tweak both the optical properties and the electronic properties just using these light pulses.
That does sound revolutionary. What was the biggest challenge, do you think? Or maybe the most surprising thing they found, getting this light-driven control to work so fast?
Well, one of the huge hurdles was probably the whole package. The fundamental concept, getting the experimental setup right, the theoretical modeling behind it. A lot of that core work was developed at Bielefeld. Dr. Tomoki Hirooka, who was actually a Marie Skłodowska-Curie Fellow in Professor Turkinovich's group then, he was the lead author. He played a really key role and mentioned how rewarding it was just seeing such a strong, clear effect triggered purely by the terahertz light.
Hmm. And those complex nano antennas you talked about, the 3D, 2D ones, I bet actually making something that precise was incredibly difficult.
Oh, absolutely. That fabrication happened over at IFW Dresden. Dr. Andy Thomas led that team. He mentioned it took a huge amount of work. They had to fabricate and test many, many different structures to really dial in the performance they needed to see this effect clearly. So definitely a big collaborative effort needing some serious precision engineering to make it happen.
Okay, so bringing it back, what does this all mean for, for you listening, for the tech you use? Because this isn't just a lab curiosity, right? This could lead to incredibly fast signal control devices, electronic switches, maybe even new kinds of sensors.
Exactly. The potential applications are really far-reaching. Think about faster data transmission, better cameras perhaps, laser systems. If you look at the bigger picture, this kind of tech could genuinely revolutionize communication systems. It could massively impact computing speeds, push forward imaging techniques,
Yeah.
and even potentially advance quantum technologies.
Right. So just to recap the core idea here, we've looked into how scientists are using these ultrafast light pulses and these very cleverly designed nanoantennas to essentially control materials like molybdenum disulfide at just unbelievable speeds, less than a picosecond. A trillionth of a second.
Yeah, and it shifts the whole paradigm, doesn't it? Away from that traditional electronic gating, which has fundamental speed limits, towards a light-driven approach, one that seems compatible with industry methods, potentially, and is just massively faster.
So this technology, it really could change the game for everything from data transfer and computing to imaging, maybe even quantum stuff, making our devices faster, more efficient than we've seen before.
And that leads to a pretty interesting thought, doesn't it? If the very fabric of our electronics, the fundamental way they operate, can be controlled by light, enabling things at speeds we previously thought were impossible. It makes you wonder, how might this shift change not just how we interact with technology day to day, but maybe what's even possible for human innovation and discovery in the coming decades? What new frontiers does this open up?